Hurricanes are just these incredible forces of nature. They're these massive, swirling engines of wind and rain that are born over the ocean. But believe it or not, these giants have an Achilles heel. So let's get right into it and figure out what that is.
And it's a really great question, right? We see these colossal storms on satellite maps, just churning with unbelievable power out at sea. But the second they hit land, it's like they start to run out of steam. So why? What is it about solid ground that can tame these absolute monsters of the sea?
Well, to really get to the bottom of that mystery, we first have to make sure we're all on the same page. We need to understand exactly what we're dealing with. So fundamentally, what exactly is a hurricane?
At its very core, it's a giant, spinning heat engine. And you got to focus on two key things here: rotating and warm ocean water. Those two elements are the absolute foundation, the DNA of what gives a hurricane its identity and its massive power. Now this is the magic number. A tropical storm can be pretty nasty for sure, but once its sustained wind speed hits 74 miles per hour, that's about 119 kilometers per hour, that's when it officially graduates. It earns the title hurricane.
And hey, this isn't just happening in one corner of the globe. It's a worldwide thing. We might call it a hurricane in the Atlantic, or a typhoon out in the Western Pacific, or a cyclone in the Indian Ocean. But at the end of the day, we're talking about the exact same kind of powerful, rotating storm. It's a global force with a bunch of local names.
All right, so how do these giants even get started in the first place? The best way to think about it is like a recipe, one with a very, very specific set of ingredients and conditions. Let's take a look at what we need.
Okay, first up, you absolutely need a huge stretch of really warm ocean water. And we're not talking just, bathtub warm. It's got to be at least 80 degrees Fahrenheit. This super warm water heats up the air right above it, making that moist air shoot upwards. As it rises, it creates this area of lower pressure down by the surface, kind of like a giant vacuum cleaner pulling in more and more air from all around it. So just remember this: that warm water, that's the battery pack. The rising moist air, that's the current that gets the whole engine roaring.
But all that rising air would just be, well, a bunch of rising air, if it wasn't for one last huge ingredient: the fact that our planet is spinning. It's called the Coriolis effect, and it basically gives all that air rushing inwards a little nudge, forcing the entire system to start rotating into that classic, iconic spiral shape we all recognize.
Okay, so our storm is born, it's spinning, it's out there on the ocean. Now let's pop the hood and see what's going on inside this thing. What are the key parts that make up a fully formed hurricane?
So when you look at a hurricane, you'll see three really distinct parts. Right in the middle, you've got the eye, which is this weirdly, eerily calm spot where the sun might even be shining. But don't let that fool you, because wrapping around that calm is the most violent part of the entire storm, the eye wall. This is where you'll find the absolute strongest winds and the heaviest rain. And then, spiraling out from there, you have the rain bands. Those are the long arms of the storm that can stretch for hundreds of miles.
And I really can't stress this enough. The whole storm is dangerous, obviously, but the eye wall, that's the zone of maximum destruction. It's just this furious, churning ring of pure power that shows the hurricane at its absolute most intense.
All right, we've got our storm. It's a beast. It's fully formed, churning over the ocean. So now we finally get to the heart of our question. What happens when this incredibly complex heat engine makes that jump from the sea to solid ground?
And really, it all boils down to two huge reasons you see right here. When it's over the ocean, it has an all-you-can-eat buffet, a constant supply of warm water fuel, and a nice smooth surface with very little friction. But the moment it hits land, both of those things vanish. Basically, the fuel line gets yanked out and someone slams on the brakes, hard.
So let's dig into that first reason a little more. A hurricane is literally fueled by all that heat and moisture it sucks up from warm ocean water. The second it slides over land, it's like someone pulls the plug on a massive machine. Its main power source is just gone, and that powerful engine starts to cough and sputter.
And then there's the second killer: friction. I mean, the surface of the ocean is pretty smooth, but land is rough. You've got mountains, buildings, huge forests. All of that stuff acts like a giant brake pad. It messes up that smooth, circular flow of wind near the bottom of the storm, weakening its spin and slowing the whole thing down in a big way.
Okay, so the storm's getting weaker. We can all relax, right? No, absolutely not.
A dying hurricane can still be incredibly dangerous, and this is a really, really important distinction to get.
See, as a hurricane grinds to a halt over land, it can just sit there and dump unbelievable amounts of rain. This often leads to terrible, widespread flooding. The swirling, unstable air is also perfect for spinning up tornadoes. And even though the storm's center is weakening, those outer bands can still carry destructive winds hundreds of miles inland. So here's the bottom line. Just because a storm isn't a Category 4 anymore, doesn't mean it's not a threat. The main danger just shifts. It goes from being about pure wind speed to being about water, flooding, and tornadoes. And that is why it is so important to keep listening to warnings from officials, even if you live far away from the coast.
So understanding that a hurricane is basically this massive heat engine that runs on water, that's huge for helping us predict what it's going to do. But it also leaves us with a pretty critical question to think about. Knowing what makes these storms tick and what makes them stop, how do we take that knowledge and use it to better protect our homes, our communities, and ourselves from their incredible and lasting power?